Today, we will prove the infamous Cantor-Bernstein Theorem. But because the proof is short and sweet, we will also talk about infinite sets, provide intuition behind Cantor-Bernstein Theorem, and demonstrate its usefulness. But before we begin, I would like to dedicate today's lecture to the people who taught me set theory. My math department advisor Solomon Pfefferman, and my honors thesis advisor Grigori Mintz. I will always admire your love of life, logic, and learning. In mathematics, we often work with infinity. For example, in calculus alone, we have expressions like n can be arbitrarily big, epsilon can be arbitrarily small, consider an arbitrary union of sets, the sequence gets arbitrarily close to some limit. However, like the novel Animal Farm, infinity is a lot more complicated than it seems. Consider, for example, the natural numbers. There are infinitely many natural numbers, and in between each consecutive pair, there are infinitely many real numbers. In fact, there are more reals than natural numbers. However, there are also infinitely many rational numbers between each consecutive pair. Yet the set of rationals has the same size as the set of natural numbers. But before one can prove any claims about which infinite sets are bigger, we need a formal way to compare them. And to find out how, we first look to finite sets for inspiration. Consider two finite sets, A and B. Recall that a function f from a to b is 1 to 1 if for every x and y in a, f of x equals f of y implies x equals y. Whereas f is onto if for every y in b, there is some x in a such that f of x equals y. If f is both 1 to 1 and onto, then f is a bijection. Consider a 1-to-1 mapping from a to b. You can see and easily prove that if there is a 1-to-1 mapping from a to b, then there must be at least as many elements in b as in a. Likewise, you can easily prove that if there is an onto mapping from a to b, then there must be at least as many elements in a as in b. So in the case f is a bijection, a and b are the same size. And from this observation with finite sets, we are inspired to make an infinite extension. Definition. We say that A is equanumerous, or has the same size, to a set B if we can produce a bijection between A and B. If A and B are equanumerous, we write A is equanumerous to B. So, for example, we can show that n cross n is equanumerous to n. Note that if you study set theory, proving that these two sets have the same size is essentially proving the rationals are countable. Theorem: n cross n is equanumerous to n. Proof: consider Fij equals 2 to the I minus 1 times 2j minus 1. Now we check that this is a bijection. So first let's check that this function is 1 to 1. Suppose fi1j1 is equal to fi2j2. Then by definition of f, 2 to the I1 minus 1 times 2j1 minus 1 is equal to 2 to the I2 minus 1 times 2j2 minus 1. Notice that 2j1 minus 1, 2j2 minus 1 are odd numbers, and thus contains no power of 2. By the fundamental theorem of arithmetic, we know the powers of 2 are equal. So I1 minus 1 equals I2 minus 1, implying I1 equals I2. Dividing out 2 to the I1, we get 2j1 minus 1 equals 2j2 minus 1, and thus j1 equals j2. Now that we've proved 1 to 1, let's prove onto. Let n be an n. First note that if n equals 1, we automatically have that f11 equals 1. So let's only consider the case n greater than or equal to 2. By the fundamental theorem of arithmetic, n has the prime factorization, n equals 2 alpha, p1 alpha 1, p2 alpha 2, times ps to the alpha s. Choosing I equals alpha plus 1, and j equals p1 alpha 1, p2 alpha 2, ps alpha s plus 1 all over 2, we can just plug it in, and we see that we have Fij equals n. Note that our choice of f relied on arithmetic intuition. But here's another classic proof that n cross n is equanumerous to n, which visualizes n cross n as a grid of pairs and then counts along the diagonals. Theorem. N cross n is equal numerous to n. Proof. Define the mapping Fij equals I plus j minus 2 times I plus j minus 1 all over 2 plus I. Like last time, we're going to prove that this is a bijection. So first let's prove it's onto. The key is to notice that along any diagonal, the sum I plus j is constant. So to make life easier, define a new variable, k equals I plus j. Then, Fij is equal to k minus 2 times k minus 1 over 2 plus I, where 1 is less than or equal to I less than or equal to k minus 1. But lo and behold, what is this? The fraction is an application of Gauss's formula. 1 plus 2 plus 3 all the way up to n is equal to n times n plus 1 over 2. Therefore, f of ij is equal to 1 plus 2 all the way up to k minus 2 plus I, where 1 is less than or equal to I less than or equal to k minus 1. Now, the next step is analogous to the first step of growing a number into binary. Subtract off the biggest power of 2 to get a remainder. But here, we subtract off the biggest k minus 2 times k minus 1 over 2 less than n to get a remainder of I. Think of this as base Gaussian. So for any n in n, choose a particular case such that 1 plus 2 up to k minus 2 is less than or equal to n, which is less than 1 plus 2 up to k minus 1. Then for the choice of I equals n minus 1 plus 2 up to k minus 2, and j equals k minus I, we have f of ij equals 1 plus 2 up to k minus 2 plus n minus 1 plus 2 up to k minus 2, which turns out it's just n. Now that we proved that the function's onto, let's prove that it's 1 to 1. Suppose f of I1j1 is equal to f of I2j2. Then, I1 plus j1 minus 2 times I1 plus j1 minus 1 all over 2 plus I1 is equal to I2 plus j2 minus 2 times I2 plus j2 minus 1 over 2 plus I2. I claim that f must map to the same diagonal. In other words, the sum I1 plus j1 is equal to I2 plus j2. Rewrite our equation in terms of k. As k1 minus 2 times k1 minus 1 over 2 plus I1 equals k2 minus 2 times k2 minus 1 over 2 plus I2. Without loss of generality, suppose k1 is less than k2. By Gauss's formula again, we can bound the left-hand side. k1 minus 2 times k1 minus 1 over 2 plus I1 is equal to 1 plus 2 up to k1 minus 2 plus I1, which we know is less than or equal to k1 minus 1. So this whole expression is less than or equal to 1 plus 2 up to k1 minus 1, which by Gauss's formula is just k1 minus 1 times k1 over 2. But obviously, by basic integer properties, k1 being less than k2 automatically implies that k1 is less than or equal to k2 minus 1, and k1 minus 1 is less than or equal to k2 minus 2. Therefore, we can further bound k1 minus 1 times k1 over 2 is less than or equal to k2 minus 2 times k2 minus 1 all over 2. Moreover, k2 minus 2 times k2 minus 1 over 2 is strictly less than k2 minus 2 times k2 minus 1 over 2 plus I2, because I2 is greater than or equal to 1. This gives us k1 minus 2 times k1 minus 1 over 2 plus I1 is strictly less than k2 minus 2 times k2 minus 1 over 2 plus I2, which is a contradiction since they are supposed to be equal. Therefore, we must have k1 equals k2. Now the proof is easy. Our equality becomes k1 minus 2 times k1 minus 1 over 2 plus I1 equals k1 minus 2 times k1 minus 1 over 2 plus I2, which immediately implies that I1 equals I2. And then J1 equals k1 minus I1, which is the same thing as k2 minus I2, which is then just J2. Notice that in the last two examples, the bijections were quite complex, and it's not obvious how we cook them up. In fact, when trying to prove two sets are equinumerous, it's possible that no bijection actually exists. Let's do a classic example. And because Cantor's diagonalization argument has been done to death on YouTube, here's a proof that uses Russell's paradox. Cantor's theorem. There is a one-to-one mapping, but not a bijection, from A to PA, where PA is the set of all subsets of A. So intuitively, this result says there are bigger and bigger infinities. Proof. Of course, there's a one-to-one mapping from A to PA. Namely, the mapping from X to the set containing X. So let's prove that no bijection exists. Suppose, for the sake of contradiction, there is a bijection F from A to PA. Then consider the collection of all elements in X such that when you map it by F, the image set f of x does not contain the original x. So S equals x in A, where x is not in f of x. Since f is a bijection, there is some y such that f of y equals s. Now we ask ourselves, is y in S? Well, if y is in S, then by definition, y is not in f of y, a contradiction. Likewise, if y is not in S, then y satisfies the definition of S, and hence y is in S, again a contradiction. So we have a y that is neither in S nor not in S, which is impossible. Hence, no such bijection f can exist. From our examples, we can see that finding a bijection between two sets can be difficult. Or perhaps, there is no bijection at all. But what Cantor-Bernstein Theorem provides is another method for proving two sets are equinumerous, so we can try attacking the problem from a different angle. Let's go back to our finite sets A and B, and instead of considering just one function, let's consider two. F which takes A to B, and G which maps B to A. If F is 1 to 1, then the size of A is less than or equal to the size of B. And if G is 1 to 1, then the size of B is less than or equal to the size of A. So again, we have the sizes of the sets, A and B, are the same. And just like how the finite case inspired us to make a definition for same size in the infinite case, the finite case also inspires the Cantor-Bernstein theorem. And the Cantor-Bernstein theorem states, if there's a 1-to-1 mapping from A to B, and a 1-to-1 mapping from B to A, then A is equinumerous to B. Of course, especially in the case of infinite sets, this is not obvious, and we need to prove this theorem. But once we have this theorem, we gain another, sometimes easier way to prove that two sets are equinumerous. But how can we build a bijection from two given 1-to-1 functions? It's absolutely not obvious. But to quote the math wizard,
Math mantra. Most mathematics come from being locked in a room and wasting tons of paper.
let's start with a simple example and keep adjusting our guess of a bijection. And when we are confident we have the right one, we toss out all the scratch work and begin our proof. So consider the following 1-to-1 mapping F from A to B, and 1-to-1 mapping G from B to A. Of course, defining our bijection j from a to b as jx equals f of x is not enough. It's 1-to-1, but not necessarily onto. So to solve the problem of onto, we consider G inverse. And then we split J so that it maps the image of G using G inverse and the rest of A using F. So J of x is equal to f of x when x is in A minus G of B, and it's equal to G inverse of x when x is in GB. Our mapping is onto by construction. However, J fails to be 1-to-1. So how can we adjust our map, J, so that to prevent 1-to-1 failing in this case? Well, like in computer science, we construct a separate if-else statement to handle this edge case. In our example, notice that injectivity fails when we have an x1 in A minus GB and x2 in GB, such that f of x1 equals G inverse of x2. To fix this problem, we want x2 to be mapped by f as opposed to G inverse. So we create a separate case. Notice that f of x1 equals G inverse x2 implies x2 equals G of f of x1. So we can create the separate case that if an element in A is of the form gf of x, where x is in A minus GB, then we map by f. Otherwise, we continue the map by G inverse. So jx equals f of x if x is in A minus GB, j of x equal to f of x if x is in G of f of A minus GB, and it's equal to G inverse of x otherwise. Note that the case otherwise is a subset of GB, since the first case is A minus GB. So mapping by G inverse still makes sense. Now, we may think we're out of the woods, but by fixing one problem, we create another. Namely, we now have elements x1 in G of f of A minus GB and x2 in GB, such that f of x1 equals G inverse of x2. But this means that x2 is in G of f of G of f of A minus GB. Generalizing, we can foresee that we'll have to construct a separate case for each element of the form G of f of G of f up to G of f of A minus GB. A fellow YouTuber gave an analogy of Cantor-Bernstein Theorem to Hilbert's hotel. To fit a new guest into a hotel with infinitely many rooms where each room is occupied, we ask each current guest to move one room to the right. And indeed, in order to make J into a bijection intuitively, like Hilbert's hotel, we are pushing our problems to the right by mapping cases where 1-to-1 failed by G of f, and those new cases where 1-to-1 property still fails by G of f again, ad infinitum. Now, before we go any further, let's make our notation easier by using recursion. Define C of 0 equals A minus GB, and C of n plus 1 equals G of f of Cn for n greater than or equal to 0. Then we can collapse our definition of J as f of x when x is in C0, f of x when x is in C1, f of x when x is in C2, and so forth, and G inverse otherwise. But this just becomes f of x when x is in Cn, where n is a natural number, or G inverse otherwise. Now that we have a worthy candidate for a bijection, let's prove it actually works. Cantor-Bernstein Theorem. If there is a 1-to-1 mapping from A to B, and a 1-to-1 mapping from B to A, then A is equinumerous to B. Let F be a 1-to-1 mapping from A to B, and G a 1-to-1 mapping from B to A, and define C0 equals A minus GB, and Cn plus 1 equals G of f of Cn for n greater than or equal to 0. Consider the function J of x equals f of x when x is in Cn, where n is a natural number, and G inverse of x otherwise. We want to show that J is a bijection. So first, let's prove it is 1-to-1. Let x1 and x2 be in A, such that J of x1 equals J of x2. Well, without loss of generality, either x1 is in Cn and x2 is in Cm for some m and n, x1 and x2 are not in Cn for any n, x1 is in Cn for some n, and x2 is not in Cm for any m. In our first case, by definition of J, we immediately have f of x1 equals f of x2, and since f is 1-to-1, x1 equals x2. Likewise, in the second case, g of x1 equals g of x2, and because g is 1-to-1, x1 equals x2. So the only real case to check is the third case. By definition of J, we have f of x1 equals g inverse of x2. But this means x2 is equal to g of f of x1. In other words, x2 is in C of n plus 1, a contradiction. So this case is actually impossible, which should be no surprise since we explicitly constructed J to avoid this case. Therefore, J is 1-to-1. Now let's prove J is onto. To prove J is onto, let y be in B. We want to find a corresponding x in A such that J of x is equal to y. We have one of two cases. Either y is in f of Cn for some n, or y is not in f of Cn for any n. In the first case, we are instantly done by definition. there is some x in Cn, and j of x equals f of x equals y. So consider the second case and map y by g. Now I claim that g of y is not in Cn for any n. Suppose otherwise, and that it were the case that gy is in Cn for some n. Note that n is greater than 0, since c0 equals a minus gb, and so cannot contain gy. Since gy is in Cn, we have y is in g inverse of Cn, but that means y is in g inverse of g of f of Cn minus 1. So y is in f of Cn minus 1, contradicting the assumption that y is not in f of Cn for any n. Since g of y is in no Cn, j of gy is equal to g inverse of gy, which is just y. Therefore, j is on 2, and the proof is complete. Here's a classic corollary of Cantor-Bernstein, in which the work required to prove two sets are equonumerous is tremendously simplified. The open set 0, 1 is equonumerous to the closed set 0, 1. Proof. Obviously, the identity map f of x equals x is a one-to-one map from 0, 1 to 0, 1. We can also construct a one-to-one map from 0, 1 to 0, 1 by squeezing the unit interval and shifting by some small constant, say 1/3. So f of x equals 1/2 x plus 1/3 is a one-to-one map. Therefore, by Cantor-Bernstein, 0, 1 is equonumerous to 0, 1. Note that if we did not apply Cantor-Bernstein, we would need to cook up a crazy bijection like f of x equals 1/2 when x equals 0, 1 over n plus 2 when x equals 1 over n, where n is an integer, n greater than or equal to 1, or x otherwise. Let's do one more classic application of the Cantor-Bernstein theorem. 0, 1 is equonumerous to 0, 1 cross 0, 1. Proof. We know that the identity mapping, which fixes the second component as 0, is 1-to-1. f of x equals x comma 0. To construct a one-to-one mapping from 0, 1 cross 0, 1 to 0, 1, we need to use the fact that every real number can be written as a unique non-terminating decimal. For x and y in 0, 1 with unique non-terminating expansions, x equals x1, x2, x3, and so forth, and y equals y1, y2, y3, and so forth, the mapping which interweaves these decimal expansions, f of xy equals 0.x1y1, x2y2, and so forth, provides a one-to-one map from 0, 1 cross 0, 1 to 0, 1. Again, if you try to construct the bijection explicitly, it is a lot more complicated. It is so complicated, I'm going to spare you the details and let you search up the solution on MathStackExchange. Thanks for listening. I hope that this lecture gives you a sincere appreciation for infinite sets and the awesomeness of Cantor-Bernstein theorem. I'll see you again soon.